Welcome back everyone. In our previous session we discussed the truncation of the dendrogram and we look at what the Ward's distance was and how to actually truncate the actual dendrogram itself to figure out what or how many clusters we should have. And after that we utilize a f-cluster function to retrieve the so-called allocation of the cluster for each observation. And after that we did some visualization that presented it this way. Makes it nice and easy, or quite kind of visually appealing to present to management, and also help us to actually understand the underlying structure as well. And we figured out that there were two ways. One is by distance, which is this one here. It's by distance, using the f-clusters by distance. Or the second way is that we use the number of clusters based on the number that we specify here. So in this session, we're going to progress a little bit further. Now we're going to look at k-means clustering, as I promised previously. What exactly is k-means clustering? Now, k-means clustering is really another unsupervised method or machine learning algorithm. So what it does is that it analyzes and find patterns or clusters within the actual data itself. It works on what you will call distance measure. A little bit more in terms of the description that's provided from scikit-learn library. First of all, it clusters the data by trying to separate the different samples, or the samples in n groups of equal variance. That's the first one. Equal variance basically means the standard deviation square. The second thing is that it minimizes a criterion known as the inertia, or within cluster sum of squares. So it's trying to minimize that, and also trying to actually separate the so-called groups of equal variance. Now in this method it requires the number of clusters to be specified. The beauty of this measure is that it scales well with large number of data. So just to expand on how does k-means clustering works, is that it divides a set of samples into disjoint clusters. And this is the part whereby beforehand you have to actually define or give it a specific number of clusters to work towards. Each are described. Now each of these clusters are described by the means of the samples in the clusters itself. Now these means are commonly called the clusters centroids. Now take note that these centroids are generally not in the so-called points from those samples, although they live in the same space. I guess let me just plot this out a little bit just to illustrate the point. If I say I have two clusters, so let's just say it's like this, all right, and then I have another clusters here. Okay, and I take, let's just say, centroids, which could very well be here, and another centroid, which could very well be here. You notice that they are in the same space, right? That part is pretty obvious. They are in the same space. So they are in this space, and these slots are in this space. But the actual centroid itself, may not be the actual sample itself. So that's really what that point here is actually saying. They are in the same space, okay, which is what this is saying, but they are generally not in one of the points. Okay, so the basic ideas of k-means clustering, let me come back, is that it aims to choose a centroid or choose centroids that minimize the inertia or minimize the within cluster sum of square criterion. So once if I identify clusters, then it tried to find a point, okay, which actually minimize the so-called sums of squares, or basically the deviation from the centroid itself. So that part works pretty much very similar to linear regression. Okay, enough of the definition itself. Let's actually look into how you actually implement this to the problem that we have previously. Now remember, we have these 5 clusters. Let's have a look at how you can actually utilize the k-means clustering to resolve this problem. So the first thing is that from the scikit-learn library, scikit-learn cluster, we import k-means. Okay, and we need to next, let's just import that first, some scikit-learn. Okay, the next thing is that we instantiate this, and k-means is equal to k-means, and then the number of clusters. Now this is the part where we don't know, so we're just gonna specify 3 to begin with, and then we fit our data after we actually have instantiated that. Okay, remember x is actually what our sample, or where our sample is. Right, so having done that, the next thing is that we need to estimate by performing the actual prediction itself, k-means, and predict x to find the actual centroid itself. Right, now let's just visualize what we've done here. X 0, that's all of the first column's data. The next one is all of the data from the second column, and then the centroid, or the centroid is the y k-means that we have estimated. This is the size of the centroid, and then the color, I'm just gonna choose Infernal. There are many of these, so you have to look up Matplotlib for that. So the centers is equal to the k-means clusters centers, and plot scatter centers, okay, 0, and centers 1, and then we choose the centroid's color to be green, and finally this make it large, and finally alpha, which is the opaqueness, to 0.7. Actually, let me correct myself a little bit. This is actually to plot all of the dots, which are these dots here, and this is actually the center, or the centroids itself, and these here from the actual scikit-learn library, or after it has actually fit the data, it actually has generated the center, or the centroid. So let's just plot this out. Okay, again, let me highlight this. Notice that this is really ugly. I don't like that, so to remove that, I put a semicolon. Okay. Now, what can you see here? You notice that there's actually I probably should put 500, makes it easier to visualize. Okay, what can you see? You can see that this is a centroid, this is another centroid, and here's another centroid. Basically, it identified 3 different clusters here. Hence, it painted 3 different colors. So it considered this and these are to be from the same cluster, and the yellow are from the same clusters, and then the pink are from the same clusters. So it locates the actual minimum, minimize the, basically find the lowest of the within cluster sums of squares, which is here for this, and here for this. Okay, now you actually start to get the idea of how that actually works. Now, why don't we actually try a slight variation of that. Instead of 3, let's just try 5. Okay, and notice that it actually find the middle of these and basically put the so-called what do you call it, the centroid on top of it. Now, we previously imported the machine learning extend, but we haven't used it, so I'm going to show you how to use it now. Import the plot the decision regions. This is pretty much the actual specific functions that I really want to use, which is quite handy. I don't have to write the whole lot. CLF is the k-means itself. Now, just to explain a little bit about this method, or this function. So we are importing from the ML extend basically the plotting function. The so-called input variables that we do need to provide is the x and the y, and also the so-called classification method, which is k-means here. The x and y, where do we get that? Is from the, let me just come back up here, what we generated before. Notice there's the x and y that we've generated before from Matplotlib, using the Matplotlib functions of scikit-learn. So let's run that, and notice that it plots it out nicely for you. 5 regions. You have 1, 2, 3, 4, 5, and it's given you a nice specific notations to go with it. Now, what if I actually go back and set that to 3? What happened? This is our plot. Notice the 3 that we observed before, and plot this out, and notice that it is segregated this way, exactly the same as this. Okay, this cluster, this clusters, and this cluster. Okay, so the next thing now is to just discuss a little bit about some challenges that you might find with k-means clustering method. One is that you might not achieve global minima. That's the first one. And the second one is that the number of clusters must be selected beforehand. So that's why what we did is that we to specify it. In the next lesson, I'm going to go into the choosing how many clusters via the elbow method. The third point here is that k-means is limited to linear cluster boundaries. Now that is one key issue that you have, but fear not, we have discussed a method to resolve this. Remember the previous section we talked about PCA. You can actually use PCA to reduce it down to, let's just say, two what you call principal components before you apply k-means to it. Now the one last thing is that k-means can be quite slow for large numbers of samples. So with that, I'd just like you to run an exercise. We talked about k-means clustering quite a fair bit in this session. So what will be actually a good exercise is to try a slightly different number of clusters. If we look at the dendrogram earlier, so 1, 2, 3, 4, 5 is one of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Try 14. And see how it actually, see if it actually can segregate those quite easily. So let's just pause the video and give that a try, and when you come back, I'll summarize the lesson. How did that go? I hope you've given that a try and gain some insights into how k-means works. I did mention that we should try 14, so since I've asked you to try, you can actually, I'll run it as well. So you notice that I didn't do too well, really. If you look at this, it's just one big giant blobs. So maybe a smaller number, it's better. And that's really one of the key challenge with k-means, is that you don't really know beforehand how many clusters you should actually really try. And that brings us to the next session, which I will talk about in the next video, which is called the elbow method. So I look forward to seeing you in the next lesson. Thank you for watching.